All right. Good afternoon, ladies and gentlemen. My name is Whitney Belkowitz. I'm the president and CEO of Intelligent Concrete. And I'd like to give you a quick peek into what we like to call the magical world of concrete, specifically looking at nanosilica enhanced pavements, paving the way for a more durable concrete. Now, before I get into the presentation, I'd like to give a quick thank you to Specification Products for paying for us to put this research together, as well as the United States Air Force due to the AFWorks program that we're a part of. And then, of course, the United States Air Force Academy and the cadets who are working with us on pavements of the future and bases of the future. Okay, so on to our overview. First and foremost, I want to give a quick background into who we are and what we do at Intelligent Concrete. Then I want to dive into the research and motivation. Why do we care about the efforts that we're putting into this and the technologies we're using to make pavements of the future? After that, we're going to dive into the meat of the presentation with the set of definitions first, and I believe those are warranted to set a foundation for what we're going to be talking about. With that, we're going to get into the analysis of our case studies, looking at two case studies. One is the Labcrete and the other is Realcrete. Then we'll wrap it up with a concise summary and open up the floor for any questions. As I said before, my name is Whitney Belkowitz. I am the president and CEO of Intelligent Concrete. I've been in the industry for 13 years trying to understand the seemingly simple yet truly complex construction material. I've been at the forefront helping architects, engineers, and ready-mix providers bring new and emerging technologies into the concrete and construction industry. You know, far too often these amazing industry-changing technologies are lost in university laboratories. And one of my favorite things about what we do is that technical transfer. We find these products that can make a huge impact in the industry and help bring them into the industry in a commercially applicable and economically feasible way. We are a technical representative for the concrete and construction industry. Okay, so on to our research motivation. Why is it that we do what we do? There is a wonderful paper that goes over 170 plus permanent facilities owned and operated by the United States Air Force and how these facilities, especially our air-filled pavements, are unsatisfactory when it comes to the high performance that we have in the United States Air Force to fight and win wars. Now, the cause of the underperforming pavements has a multitude of reasons. Whether it's the original mix design, it's the construction, the chemical reactions, that physical and chemical attack, that wear and tear that we see from excessive use and heavier loads. Ultimately, an enhancement of the current concrete that we're using for air-filled pavements is needed, and it's needed to reduce something called foreign object damage. Basically, it's the rocks and spalls on the concrete surface that's falling apart to create something called foreign object damage, where a handful of this stuff could really debilitate our inventory on our runways, pavements, and taxiways. So what we want to do is enhance concrete so that there's less maintenance, so that we have a lower amount of air-filled shutdown time due to sweeping for that foreign object debris. And of course, so we reduce the amount of failures that we see on our airfields to our Air Force inventory, our planes that complete the missions. And the harsh reality to the U.S. Air Force is that our airfield's durability needs to be dynamically changing to answer the multitude of conditions that we see, not only from snow removal, but also from de-icing salt and brine, as well as the breakdown, the reduction in service life, when we have that combination of chemical and abrasive wear from aircraft and the impact of the chemical and physical attack that goes into the foreign object debris. And how do we solve this problem? That's the whole purpose of this presentation. More importantly, that's the work that we're doing with SpecPro, the Air Force, and the Air Force Academy. It's using nanosilica to make concrete stronger and last longer. So for those of you that don't know, nanosilica is a colloidal dispersion of nanosilica-sized particles. Now, these dispersions can be clear to milky and can have a surface area anywhere between 800 and 5,000 meters per square gram, and a solids content that generally ranges between 15 and 50%. And if you've never seen it before, you shouldn't be surprised that it is in a liquid dispersion. Now, when people ask me, what is this nanosilica, I've got to give them a frame of reference. And more often than not, the reference that I use is Class F fly ash. So here we have a scanning electron microscope image of some Class F fly ash, and it looks like that, those ball bearings. And it has a silica surface area that's reactive enough to induce pozzolanic reaction, but that nano silica is a more pure form of it. And of course, if you look at the scales, it's 1,000 times smaller. That's why it's so important. We're having different effects on our hydrated cement matrix. So now just for a reference, a human hair strand is 100,000 nanometers in diameter. So it's 1,000 times smaller than that. Now, before we get into our case studies, the secret behind this is getting the nanosilica to do its job. It's properly dispersed throughout the concrete. Out in the field, we don't have fancy pieces of equipment to identify dispersion properties. We have to identify effectiveness through performance. So to get that performance, we do the following. We add the nanosilica at the tail end of mixing. We mix it for 70 to 100 reps. And in doing so, it fits into the normal critical path of batching concrete to leaving the plant. Okay, so getting into our case studies. What we're looking at here is actually a driveway in Black Forest, Colorado. A friend of ours was called in to do an inspection, and he called us in to come and see what he was dealing with. And basically, the entire surface of this concrete driveway was breaking down, and that was just after one season. This right here is a picture of decracking at Peterson Air Force Base. So the reason we were at Peterson Air Force Base, John's best friend was one of the military aides for, I think it was President Obama. This was a few years ago. So we're out there, it's summer, I'm pregnant, I'm always pregnant. And I'm always pregnant in these stories. Anyways, we're out there and we're watching Wesley come off Air Force One, and it's just amazing. He's in his Air Force blues. You know, we're so proud. We're so impressed. And he, you know, comes and walks down and gets in his line. And then President Obama starts coming off Air Force One. And it was cool, like to see Air Force One, to see the president. And I turned to, look at John and just kind of have this moment, like, how neat is it that we're here? And he is crouched down on his hands and knees, taking pictures of concrete, that wonderful man. And I shouldn't have been surprised. He does that often. But anyways, so he's taking these pictures. So this air-filled pavement is just falling apart, exhibiting high degrees of foreign object debris. And I would love to tell you that this is the only joint that we saw cracking like this, but every single joint that we saw there, it looked the same, even the joints and the pavements that were directly under Air Force One. So what we decided to do was partner with a local ready mix provider. And it's somebody who had tried to deal with this de-icing, salt and brine issue. And this is the mix that we used. So if you're checking out this mix, I mean, you can see that there's quite a bit of Portland cement in there. There's also a good bit of aggregate, and then we used a high range water reducer and an air entraining agent. So we cured these samples for 28 days before we actually kind of started our testing, and we let them cure in a calcium chloride bath. After that 28 days, we started curing the samples, and bear in mind, there were like 60 samples, maybe more. We were curing them in a mag chloride bath. So for those of you that don't know, that don't live in areas that get a lot of snow, mag chloride is the stuff that they spray on the road to help with de-icing. So we're doing these soaks. We run a full gamut of tests to include mass loss, and this was a modified version of ASTM C672. So we are doing a 16 to 18 hour freeze and then a 6 to 8 hour thaw in this mag chloride brine. And we were doing that on all the samples that we were testing. So we also conducted compressive strengths and abrasion as well, and we'll see that data here a little bit later. But what you can see is the mass lost, that the reference is losing a lot more than the nanosilica enhanced concrete. And that's one of the things. We're reducing permeability. We're increasing the backbone of the concrete strength. So there's a higher resiliency to that de-icing brine attack compared to a reference. And it was still, a good concrete to begin with. So here at our day zero mark, and that was the 28-day cure in the lime water bath. We've got our reference breaking at 5,600 PSI, and our nanosilica enhanced concrete is breaking at about 6,200 PSI. Now, bear in mind, we were just using the Nano Silica to really increase our durability. We didn't use a high dosage to give it a huge boost in strength. We were just trying to make it a more durable concrete. And as you can see over time, that reference concrete that doesn't have the Nano Silica in it, we're losing strength over time. I mean, we get to that 90-day mark and you're just seeing that reference get weaker and weaker. And the the samples that had the Nano Silica in it continue to increase in strength until we get to 90 days, and then they just kind of plateau. So they did start decreasing a very small amount, and something to keep in mind. I mean, we are working with concrete. There's a certain service life to it, especially when it's in a really harsh environment. But the fact that it's doing that much better than the reference, I mean, that speaks volumes. Okay, so the other test that we ran was the ASTM C779 Procedure C. So that's abrasion resistance. And for those of you that don't know, you're running this test, these samples for 20 minutes. So we've got a 26-pound force that's pressing down on the concrete. You've got 9 steel balls that are rotating at, I think it's 1700 RPM with a bunch of water. And then we're doing measurements every 50 seconds, monitoring the depth of wear to 0.0001 inches. And over this 20-minute test, you can see that the reference concrete is losing up to 40 to 50% more depth of wear than the Nano Silica enhanced concrete. And I'm not blaming the concrete. Remember, this concrete's been soaking in a mag chloride brine for the last 56 days. So it's a nasty environment that's going to make the concrete softer and less conducive to physical attack. Now, the Nano Silica concrete is locking in that aggregate. It's increasing the densification, and all that leads to a concrete that's stronger and under these abrasive forces lasts longer. And then when we get to our 90 days, I mean, that's where you really see a huge impact. You know, we got anywhere from 75 to 80% increase in resistance when we're comparing the Nano Silica enhanced concrete to the reference. So moving on to case study 2, there is something that we did years ago for John's PhD, and very successfully. You can actually read a paper. It's in Concrete International. But the important piece that's not in the slide, and we kind of mentioned before, is that it's very easy to get the Nano Silica into the back of a truck. It's also easy to place the concrete. And we easily made our 24-hour strength and our 28-day strength without any issues. But one of the questions that we constantly get asked, and it's anytime you're putting a new technology in concrete, is what's this going to do to my concrete in 5 years? Well, that's what we did. We went back 5, 6, 7, and 8 years later and took pictures of the concrete. And, you know, you can see when you're comparing to the reference almost looks like an exposed aggregate sort of look. I mean, you can see where the tire tracks have worn down the concrete, and then you look on the right and it looks like, you know, it's almost brand new concrete. You can see skid marks, but there's really very little wear and tear on that concrete. Okay, so our next step. What I wanted to show you today was a lot of information, short-term, that over 100 days, that shows the impetus behind using this technology in concrete. You know, we had some great results, not only with the mass loss when we're dunking this stuff and allowing it to freeze and thaw in mag chloride, but then running compressive strength on the same samples and abrasion resistance on the same samples. And ultimately, both of those, all 3 of those data sets show that using Nano Silica enhanced concrete is the way to go. You know, we've been working on this effort for a long time, not only to get Nano Silica into the back of a truck, but also to make it more palatable, you know, colloidal silica additives more palatable for the industry and the ready mix provider to accept. And at this point, we're just starting to see light at the end of the tunnel to get this new ASTM created. So the next step is identifying the need of the industry. You know, we've got real problems with few viable solutions. There's a limitation on our mature technologies, our class of fly ash, our microsilicas, and so on. Our quality aggregate supply also happens to be dwindling as well. And with these fly ashes, we need a real solution and a timely solution. Now, Nano Silica has not only shown through successes in university basements and university labs, but also commercial labs all over the world. It has a wide variety of commercial successes. So what's the next step? It's convincing the industry to give it a try, to show how to use this stuff in the back of the truck and to save the world with all the concrete in it. I would like to open up the floor for any questions.
That slide in front of y'all,
Oh,
it's from Denver International Airport. We did a few parking lots out there. Okay, so.
oh, how old were the Peterson pavements?
Oh gosh, I mean that's a hard number because a lot of it has been replaced piecemeal. I want to say the majority of it was placed in like the 60s or replaced in the 60s and 70s.
Jeez.
You know, we're working on an airport right now from the Air Force that was placed in the 1940s, and they're just replacing it right now. So not fairly old, could be old. It was just happening all over the runway, so it's almost irrespective. Tom also asked, how much longer do you need to mix the Nano Silica? I mean, it's just like putting any other
Admixture in at the end.
Yeah, nothing more than that. Okay.
Cool.